This video is good. It's just going to get you set up for the lab we're going to do on Beer's Law. It's called the determination of the copper content in brass using UV visible spectroscopy. So you're going to all be given a brass object, whether that be a screw or a 22 gauge rifle shell. If you want to bring in a brass object from home, you certainly can to test out its brass content. There are 3 stipulations. If you bring in a brass object from home, the first stipulation is it's going to get destroyed. So don't bring something you really care about. The second stipulation is that it has to be pure brass, so no impurities, because I don't know how those are going to react with the nitric acid, and we don't want to produce toxic stuff. The third stipulation is that its volume has to be less than 10 milliliters. So it has to be able to fit into a 50 milliliter volumetric flask. So if it meets those stipulations, you are free to bring in your own brass object. I will have ones for every group if you don't bring them in. So we're going to determine how much copper is in brass, and we're going to use UV visible spectroscopy. So UV visible spectroscopy is just another word for colorimetry. So spectroscopy, scope in Greek means to look at. Spectro is just the spectrum. So spectroscopy is a way of looking at a certain part of the electromagnetic spectrum. And in chemistry, there are a lot of different kinds of spectroscopy. The one we'll be focusing on in this lab is UV visible spectroscopy. So we're going to be looking at the ultraviolet and the visible parts of the electromagnetic spectrum. Now, since another word for visible light is color, we can also call UV visible spectroscopy colorimetry. So we're going to be using the colorimeters for that. So let's just talk a little bit about our lab. We're going to be expressing the percent mass, or sorry, the copper content in brass as a percent mass. We'll also express it as a mole fraction, but the most basic result we're going to get is the percent mass of copper in the brass object. So if we remember, percent mass is just equal to the mass of copper divided by the mass of the brass object times 100%. So, in order to calculate that in the lab, we're going to have to record the mass of the object. That's very important because we're going to destroy the object in this activity. So if you forget to record the mass, that's going to be a problem because it won't be around after the lab to record. So the first thing we got to do is we got to record the mass of the object. Well, then we got to find the mass of copper. You can't exactly measure directly the mass of copper in the object because the copper is mixed in with the zinc at an atomic level. Remember, an alloy kind of looks like this, where you have copper atoms and you have zinc atoms, and they're just kind of next to each other. So we got to somehow find a way of separating the copper from the zinc. Okay. Now, when our brass screw or key or whatever it is in its solid form, it's going to be very hard to do that because the atoms are just kind of mixed together. So what we're going to have to do is somehow we're going to have to isolate the copper from the zinc. And we're going to do that by oxidizing both of them. Okay? And the material we're going to use to oxidize them is nitric acid, HNO3. I'll explain what that graph is doing up there in a minute. But we're going to use nitric acid to oxidize both the copper and the zinc. So now, instead of copper atoms and zinc atoms in this solid brass screw, we're going to have copper plus 2 ions, plus 2, copper plus 2 ions. It's a little larger. And then we're going to have zinc plus 2 ions. And those are going to be floating around in water. Well, you may think, Mr. Pell, what have you done? You haven't really separated the copper from the zinc. The copper ions and the zinc ions are still floating around in water. But the cool thing is, when we look at the absorption spectrum for copper 2, so that's what this graph is. The absorption spectrum for copper 2, we look at the wavelengths at which copper 2 nitrate dissolved in water will absorb light. If you measure between 600 and 700 nanometers, you see that copper ions absorb red light. So that's going to make them look blue. Zinc ions do not absorb light in the visible range. So, if I dissolve my copper and my zinc in nitric acid, if I have a nice little flask with copper ions and zinc ions floating around, and I measure how much red light that flask absorbs, that is going to be directly proportional to the concentration of copper ions in my sample. Okay, so I need to find the percent mass of copper, which means I need to find the mass of copper, which means I need to find some way of isolating the copper from the zinc. I'm going to do that by dissolving both of them in nitric acid. The solution is going to turn blue, and I'm going to measure how much light that blue solution absorbs, how much red light that blue solution absorbs, in order to relate that to the concentration. So another thing I've got to record is the absorbance, but I'm going to have to do that in a very special way. So to determine the concentration of Cu, I've got to find the mass of Cu. That's what I got to find before then. Now, in order to find the mass, I'm going to have to know the moles of Cu. And in order to find the moles, I'm going to have to know the concentration of Cu and the volume of Cu, of the Cu solution. So that means that I'm going to have all of my copper 2 solution, I'm going to put that in a 50 milliliter volumetric flask. And I'm going to have a blue copper 2 solution. So this is my copper, my screw that's been dissolved in nitric acid. I'm going to put it in a 50 milliliter flask and dilute to 50 milliliters. So that way I know the volume of the copper solution. And then I'm going to have to figure out the concentration. Now the concentration is going to be found using Beer's law. So I'm not going to record the concentration directly because I don't know it, but absorbance is equal to A, B, C. So if I measure the absorbance of my dissolved screw solution, or dissolved brass solution, using my colorimeter, I measure the absorbance that is proportional to the concentration. B is the path length, that's going to be 1 centimeter. And now the only thing I need to do to ultimately find the concentration, which is going to allow me to find the moles, which is going to allow me to find the mass, which is going to allow me to find the percent mass, which is what I'm looking for. I only need to know the molar absorptivity value of the copper nitrate. Now that I don't know, okay? So if we can see, I have concentration. If I know concentration, I can find moles. If I know moles, I can find mass. If I know mass, I can find percent mass, which is what I'm looking for. But in order to find concentration, I need to find this molar absorptivity. So how am I going to find the molar absorptivity value? So then that's going to lead to the second part of your experiment, which is going to be to do a serial dilution. So let me just show you what that's going to look like. So you're going to have a known concentration of copper nitrate. Known molarity. You're going to take 10 mils of that and put that in one test tube. You're going to take 8 mils and another, 6 mils, 4 mils, and 2 mils. And then you're going to go, so that's Cu plus 2, copper nitrate. And then you're going to take H2O. You're going to add 0 mils, 2 mils, 4 mils, 6 mils, and 8 mils. And so you're going to do a dilution of that copper 2 solution. So then you're going to essentially have 5 different concentrations of copper 2 nitrate where you know the concentration. So in order to do that, you're going to have to record the precise volumes of copper nitrate solution you use, and that's called a standard solution, and H2O, and you should be able to get 3 sig figs on that, so to the nearest 0.01 milliliter. So you're going to have to record the precise values. So use the values I wrote as a guide. So use 10 mils, about 10 mils of copper 2 plus, about 8 mils in the second, about 6 mils, and so forth. But you will not get precisely those amounts. You'll get, a couple hundredths off. So just record exactly how much you got, because you want to have as much precision as possible. Then you're going to take those each of those solutions, and you're going to record the absorbance in your colorimeter. So record the absorbance of each solution. So then what you're going to be able to generate is a graph that looks kind of like this that I'm circling here. So you'll have the concentrations from knowing the volumes and knowing the initial concentration. You'll know the absorbance because you measured it with the colorimeter, and then you'll be able to plot a graph of all the different absorbance values plotted against all the different concentrations. So if absorbance equals molar absorptivity times path length times concentration, that means that provided this line on this graph here goes through the origin, that means that the slope of the line is equal to A times B. And if we know B, the path length, is just 1 centimeter, then we can cross that out because it's equal to 1. So our slope is equal to the molar absorptivity. All right. So we're going to find the molar absorptivity using this serial dilution method and recording the absorbance and finding the slope of the line. From there, we're going to use Beer's law to find the concentration, C, of our unknown solution. From there, once we found the concentration of the unknown solution, so the solution with the brass object in it, we are going to use that concentration. We're going to multiply by the volume. So 50 milliliters in that Erlenmeyer flask to find the moles of copper in our original brass object. Then we're going to use that to find the mass of copper in our original brass object, from where we can find the percent mass of copper in our brass object. Okay? So, as you can probably tell, this lab is going to be a lot more complicated than any lab you've done in honors chemistry. There are multiple steps that you need to figure out how to record in order to get the results you want. And each step, you've got to make sure that you're recording the correct value to the correct number of sig figs, and part of your grade will depend on that. So if you feel a little overwhelmed, this is fine. This is probably a more involved lab than you've ever done. We'll have a chance to talk about this lab in class, next class, and I'll be able to answer any questions you have, and I'll give you a chance to kind of work through the pre-labs together. What I'd like you to do is make sure you understand each step that I've explained, and if you don't, make sure you have a few questions on it. And then, after that, just make sure that you know what values you're going to need to record in order to get good results. So I hope that made some deal of sense. Again, this process is going to take a little while to understand and master. And I don't expect you to have it all mastered. That's why we're going to be working through this together in class. But please, I hope you took good notes on this, and we'll discuss this a little more. Have a great night.